This video, we're going to talk about improper integrals of type 2. And there's really 3 cases to consider. All right, so the first, assuming f is continuous everywhere from A to B except at B, so not on that right endpoint, not at the right bound of our integral. That's an improper integral when that happens. And you have to pay attention now, because up to now you haven't really considered that perhaps. Now you have to look at the bounds and make sure that your function is actually continuous with all the values on that bound. So if it's discontinuous at the right bound, so the right endpoint of this interval, then this improper integral equals the limit as t goes to b from the left, right? We're coming at values from the left of a up to t of x, again, provided converges to that limit. We could also have a discontinuity at the right endpoint of the interval, the left endpoint of the interval, and the lower bound of the integral. There's a discontinuity there. It's an improper integral, and we say this improper integral equals the limit as t goes to b. This time a. This time we're going to go towards a, and we're coming at it from the right? We're pushing values from b down to a from the right. And this integral is t up to b, f of x dx, and again, provided this limit exists. As always, limits have to exist in order for this to be true. Okay, so as long as you look at those bounds and you say, hey, it's not defined there on the left or it's not defined there on the right, it's pretty seamless to move to this process. The trickery is when you're not paying attention and there's some discontinuity somewhere in between, right? So if you're not looking and you have some integral, f of x dx, where there's some value in between a and b where there's a discontinuity. Okay, which means you then would split it up into 2 improper integrals, and you would have to investigate each one of their limits individually, and if they are both convergent, then our improper integral of this type is also convergent and converges to the sum of each of those values. Okay, so let me just show you an example where that might come into play and startle you, right? So if you had something like negative 2 up to 5, 1 over x dx, and you were looking at that, you say, oh, it's defined at negative 2 and it's defined at 5, and that's great. But look, we got a discontinuity at 0. Okay, so you have to be wary now whenever you see a definite integral. Is it, in fact, defined for all values on that interval? Okay, so let's just do an example in general from beginning to end. Let's say we are, considering the integral from 2 up to 5, 1 over the square root of x minus 2 dx. Now, mind you, this has a problem at 2. Right? 2 is a problem, 2 is a problem. I wanted that to change colors. So if we plug in 2, we get a 0 in the denominator, and it's a problem. Now, if I pick values bigger than 2, then what's under the radical stays positive, and we're good. So that's our only point of discontinuity. This is a type 2 one, and we will consider the limit as t goes to 2 from the right, of the integral of t up to 5, 1 over the square root of x minus 2 dx. Okay? Now, we're now just going to consider this this definite integral. We may have to do one of our techniques. In fact, I see that a u substitution is in order. So we will say u is equal to x minus 2 du is dx. So this integral becomes, really, I'm going to just do the indefinite one, 1 over u to the 1/2 du. So that's not so bad. If I actually find that indefinite integral, it's u to the negative 1/2, right? So that becomes 1/2 over that, right? 2u to the 1/2. Now, if I go back to my original, which is the square root, so the square root of u, or the square root of x minus 2. Okay, so now I can go back and consider this limit, the limit as t goes to 2 from the right of 2 square root of x minus 2, and we got to evaluate it from t up to 5. All right? Still not ready to take the limit. I still got to do the evaluating of the bounds. So 2 times the square root of 5 minus 2, which is 3, minus 2 times the square root of t minus 2, right? Now, as t goes towards 2, this little piece goes to 0, and this guy is unaffected. Boom. So what do we say? We say this improper integral right here converges to that. Dun, dun, dun.